This video lesson is about conservation of momentum. By the end of this video, you should be able to describe the interaction between two objects in terms of the change in momentum of each. You should also be able to compare the total momentum of objects before and after they collide. And finally, you should be able to state the law of conservation of momentum. When we talk about conservation of momentum, we're focused on the collision between two objects. If no external forces are acting on a system, we can say that the total momentum of the system will not change. Another way of saying that is that momentum is conserved for every isolated system. The total momentum of the system has the same value before and after the collision. How is this possible? Well, we need to go back and look at Newton's third law. We know that for every action, there is an equal and opposite reaction. So in other words, the forces acting on object 1 and object 2 are going to be the same. If you stretch that a little bit and think, that also means that the time that the two are touching is going to be the same as well. The impulses acting on each object involved in a collision are going to be equal in magnitude and opposite in direction. In terms of momentum, the momentum changes are going to be equal. What one object gains in momentum, the other object loses in momentum. So the magnitude is going to be the same, but it's going to happen in an opposite direction. When objects collide, we typically put them into two different categories. One type of collision is an elastic collision, and that's a case where the objects are going to bounce off of each other. If you watch that animation at the bottom of the screen, you can see that those cars are involved in a collision. Okay, but the small car bounces off of the moving truck. One condition for an elastic collision is that kinetic energy is conserved. Kinetic energy is simply the energy of motion and is shown by that equation on the screen. A second type of collision that we often talk about is an inelastic collision. In an inelastic collision, the objects are going to stick together after the collision and move as if they were one object. If you watch that animation going on at the bottom of the screen, this time the small car sticks to the moving van and they travel together as one object. What does this look like mathematically? Okay, let's take a look at an elastic problem first. So we've got a large truck that's going to hit a small stationary parked car. One way you can choose to set up these problems is to organize your information in a table. Since the momentum is conserved, we know that anything that happens before the collision is equal to anything that happens after the collision. So what I'm going to do is I'm going to find the momentum of both objects before they even collide. So if I take a look at the truck has a mass of 3,000 kilograms and a velocity of 10 meters per second. That gives us a total of 30,000 kilogram meters per second. The parked car, if I find its momentum, we've got 1,000 kilograms, but it's not moving, so it has 0 momentum. If I add those two together, we get a total momentum of 30,000 kilogram meters per second. Now what the law of conservation of momentum tells us is that total before has to equal my total after. So momentum is conserved, the sum of those two momenta have to add up to be that same number. So now let's look at what's happening to these vehicles after the collision. Well, we know that our truck has not changed its mass, but our goal is to find its velocity. If we figure out the momentum of the car, we've got its mass times its velocity. Multiply those together, we can see that we have 15,000 kilogram meters per second. To solve for V, I'm going to look at just what's happening after the collision. So we've got our momentum of the truck plus our momentum of the car has to equal 30,000 kilogram meters per second. Working through the algebra, you can see that we're going to get a velocity of 5 meters per second for the truck. So the truck had to have slowed down in order to transfer some of its momentum to the parked car. Again, organizing your information in a table is one way that you can organize your work. If you like an equation, okay, let's take a look at how we would show that down here. Pick one object to be the object 1, I'm going to call that my truck, plus the momentum of the car has to equal the sum of their momentum after. Mass of the truck is 3,000 kilograms times its velocity of 10. Since the car is not moving, its momentum before the collision is 0. After the collision, we don't know the velocity of the truck, but we do know the momentum of the car. That's how it would look in an equation form, and you can see we're going to get the exact same answer regardless of the way that you choose to set up the problem. Let's take a look at an inelastic problem. Okay, so we've got an astronaut that's stranded in space, and the only way for him to get moving is for some kind of a collision to happen. So he's got a friend that's going to bump into him and set the two in motion. I'm going to do the same thing. I'm going to show you how to set up the problem using a chart, and then how to set it up using an equation. Okay, so let's take a look at astronaut 1. All I'm doing is I'm looking at the momentum of each object before. So my first astronaut has a mass of 65 kilograms, and he's moving at 8 meters per second. Multiply those two together, and you get a value of 520 kilogram meters per second. Astronaut 2, he's the one that's stuck there. So he's got no momentum, or in other words, a momentum of 0. Add those two values up, you get a value of 520 kilogram meters per second. Law of conservation of momentum tells us that those values before and after have to be equal to each other. After the collision, astronaut 1 has a certain velocity. We don't know what it is. Astronaut 2 also has a certain velocity, but it just so happens to be the same as astronaut 1 because they're going to stick together and travel as one object. So focusing on the math for the second part of the equation, we've got the momentum for the first plus the momentum of the second has to equal 520. Okay, combine your terms, rearrange the equation, solve for v, and you're going to see that you get 3.71 meters per second. The way that looks in an equation form is this. The two objects are separate before the collision, but then they have a combined mass traveling at the same velocity after the equation. Putting in my numbers, I've got astronaut 1 plus astronaut 2 is equal to their combined masses times their velocity. Again, either way you choose to set up the problem, you're going to get the same answer regardless of how to set it up. One of the keys is to figure out is something moving or not, and if it's not moving, your momentum is 0. That makes it nice and easy to put it into the problem. If it is moving, you just have to include its velocity in part of your problem. Okay, here's a summary of all of the equations that we've dealt with so far. If all I want to do is find momentum, it's as simple as taking mass times velocity. An impulse, however, is an object's change in momentum, and we can represent that several different ways. A change in momentum simply means that it's the final momentum subtracted from the initial momentum. If we're changing the momentum of an object, though, what we're really changing is the velocity of the object. So we can factor out mass and just set that equal, we can factor out mass and just multiply it by our change in velocity. In order for an object's momentum to change, though, what we're really doing is applying a force over a period of time. In terms of conservation of momentum, the way that we can show that with equations, it's still our initial momentum equals our final momentum. But if it's an elastic collision, it looks something like this, because the two objects are separate before, they stay separate after. If it's an inelastic collision, we've got separate momentums before, then they have a combined momentum after. Now this before and after is just relative. Technically, this could be before, and this could be after if you want to. In a situation like this, maybe you're holding something and you throw it. Okay, that would be an example where this equation is just switched around. We tend to call those problems explosion problems. Make sure you have all of these equations in your notes for easy reference, and come ask.